Welcome to lecture series on graph data structures. In today's lecture series, let us see the graph terminologies. So, before looking into the graph terminologies, let us be clear about one thing. So, what actually a graph is? Consider a social media network, be it Facebook or LinkedIn or any other social media platforms. All the entities in the social media platform, like the participants or the events we post or the photos we post, the albums we create, all those entities are considered as nodes. And relationship between the entities are represented in the form of edges. For example, if I'm giving a friend request to a person, so the two persons A, let us say a person A is giving a friend request to person B, or a person A is getting connected with person B. So these two persons A and B are considered as nodes, whereas the relationship between these two persons are treated as edges. So whenever we add a new person to our friend list, or whenever we add a photo to our album, whenever we host an event, all those things are uh, represented as nodes, and a new edge would be created each time for that relationship. So simply, social media sites such as Facebook can be termed as a collection of nodes and edges. So hope you're clear how this social media platform can be represented using nodes and edges. Now let us see what a graph data structure is about. So graph data structure can be defined as a formalism of representing the relationship between various entities. As we have seen in the previous example, the entities are the persons involved. For example, if we take our friend list, the entities are the persons involved. So these entities are called as nodes, and the its relationship or the connection between these edges, or sorry, the relationship or the connection between these entities are represented in the form of edges. So here 0, 1, 4, 3 and 2 are the various entities. So these entities are termed as vertices in graphs, and the relationship or the connection between these vertices are represented using edges. So graph is a collection of vertices and edges. So V represents the set of vertices, whereas E represents the set of edges. So hope you are clear about what a graph is about. So we have various types of graphs, like connected graph, disconnected graph, uh, and in the connected graph itself we have strongly connected, weakly connected, directed graph, undirected graph, and directed acyclic graph. So cyclic graph, weighted graph, unweighted graph, and many other types of graphs are there. So let us see one by one. So initially, let us see what a directed graph is about. So if you could see, each edges are represented with an arrow mark. So in the previous example, or in the previous graph data structure definition that we have seen, we do not find any arrow mark in the edges. So if the edges represent a direction, that particular graph is called as directed graph. Here, take two vertices. For example, let us, in the first figure, let us take the vertices A and B. There is a connection from A to B. So here the vertex A is called your source vertex and B is called your destination vertex. So for better understanding, take two other vertices C and B. So we do not have any edge flowing from B to C. We only have edge flowing from C to B. So the C is the source vertex. Source vertex represents the starting point of the edge, or the starting point of the connection, and B will be your destination vertex. So B is the ending point where the edge terminates, or where the connection ends. So this type of graph where all the edges are directed, or all the edges shows a direction, is called as directed graph or digraph. So directed graph is also called as digraph. Here we have two types, two things. One is in degree and out degree. So before looking into what in degree and out degree is about, so let us see what a degree is. So degree represents the number of vertices that is incident on a particular, number of edges that is incident on a particular vertex. So degree represents the total number of edges incident on a particular vertex. Incident is flowing towards a particular vertex. Since this is a directed graph, if you take the vertex A, how many edges are incident on A, or how many edges are flowing towards A? Only one. Yes, so from B we have only one edge which is flowing towards A. So the in degree of A is 1. Similarly, out degree represents the number of edges coming out of A. So how many vertices are coming out of, how many edges are coming out of the vertex A? Only one. Yes. So only one vertex edges coming out of the vertex A, and it is flowing towards B. So the out degree of A is also 1. Now from the first figure, tell me the let us tell me, can you tell me what the in degree of vertex B is? See how many edges are towards the vertex B, one from A and other one from C. So in degree of B would be 2, and how many edges are moving out or going away from B? Only one edge. So out degree of edges, out degree of the vertex B is 1. So hope you are clear what in degree of a vertex and out degree of a vertex is. So we have seen what a directed graph is. Now undirected graph is a graph where the edges have no specific direction. In directed graph, all the edges will have a specific direction, and that is why it is called as a directed graph or a direct digraph. Whereas in case of undirected graph, the edges will have no specific direction. So these edges can be considered two-way. If you take the edge between vertex A and C, the edge flows from A to C as well as from C to A. So these edges in undirected graph are considered two-way. So we can write the edges U comma V or V comma U. So edges are represented as pair of vertices. The source vertex comma the destination vertex gives you the edge. But only one edge we can represent in the total set. So we cannot represent both the edges. Since there is only one path between A and C, only one set of edge, either A comma C or C comma A, can be represented in the final edge set. So here in the previous directed graph, we can only term in degree and out degree. Whereas in case of undirected graph, we can term the degree of a vertex. So degree of the vertex represents the total number of edges that a particular vertex contains. Or it is also represented in another term like total number of adjacent vertices a particular vertex is having. So first let me tell you what the first point is about. If you take the vertex A, how many edges does that have? There are two edges. Yes, from A we have two edges, one to C and one to B. So degree of the vertex A is 2. And adjacent vertices is how many vertices are connected to A. So that will give the number of adjacent vertices. So here, what are the adjacent vertices of A? B is connected to A and C is connected to A, directly connected. So there should be an edge between A and C. If there is an edge between any two vertex, those two vertices are considered as adjacent vertices. Here if you see, there is an edge between A and C and there is an edge between A and B. So A and C are adjacent. Similarly, A and B are adjacent. Likewise, there is an edge between B and C. So B and C are adjacent vertices. So total number of adjacent vertices or the total number of edges gives the degree of that particular vertex. So here degree of A is 2, degree of B is 2, and C is 2, and C is 3. Sorry, we have 3 edges, right? One to D, one to A, and one to B. So degree of C is 3. Whereas that degree of vertex D will be only 1 because there is only one adjacent vertex, which is C. So hope you are clear with what degree of vertex is. So next we see what a path and what a cycle is. So in the previous graph, previous two examples, we are discussing about what an edge is. So edge represents the direct connection between any two vertices, whereas path is different. Path is, for example, if I want to check if there is a path from Seattle to Chicago, so we can define it like if there are connected vertices in this path. So, is there a way I can reach Chicago from Seattle? Yes, I can reach Chicago from Seattle via San Francisco Dallas, or through San Francisco, Salt Lake City, or through Salt Lake City alone. So there is a path, there is a connection, though it is not directed connection, at least there is a connection or a path between Seattle and Chicago. So this is how we determine if two vertices are having a path or not. And cycle is that if that particular, if let us take two vertices, v0 and vn, if the path starts from the vertex and it ends in the same vertex, means that particular path is called as cycle. So here, uh, let us take two here, what is the cycle? Let us take V0 and V1 both as C-tail. So from C-tail we can go to Salt Lake City, and from Salt Lake City we can go to Chicago, Chicago to Dallas, from Dallas to San Francisco, and from San Francisco to C-tail again. So this, though it is considered as a path, this path is called as cyclic, and this type of graph is called as cyclic graph. So in the previous examples where we are discussing about the type of graph, now you can see what cyclic graph is about. So this is a directed cyclic graph. If you, at least there should be one cycle. It is not essential all the paths should be cyclic. If there is at least one path which is cyclic, then that particular graph is called as cyclic graph. So here, first three vertices form a cyclic path. So this graph is treated as cyclic graph. And acyclic is one if there is no, at least no one path which do not have a cycle, then particular graph is called as acyclic. So acyclic is that there should not be any one path where a cycle is formed. So such kind of graph is called as acyclic graph. And if that graph is directed, then it is called as directed acyclic graph. That is, if there is no cycle formed in a directed graph, it is called as directed acyclic graph. So let us see what it is now. Here, see, uh, this picture is given for better understanding of paths and cycles. Now take the vertex A and D. This is a directed graph, obviously, so you are aware of it, I suppose. Is there a path from A to D? So I'm not talking about the edge here, so I'm talking about the path. Is there a path from A to D? No. Yes. Why? From A we can go to B, from B we can go to C, but there is no path to reach D from C. Similarly, if I want to reach D from B, also there is no path. So I'm able to go to B from A and to C alone. I'm unable to reach D. So there is no path from A to D. Similarly, the second question here is, does this graph contains any cycles? Check. Is there a cycle between A, B, D? No, because there is no H between A and D. So the vertices A, B, D do not form a cycle. Is there a cycle among the vertices B, C, and D? Again, the answer is no. Since this is a directed graph, there is no cycle. So from D, we are reaching B from B to C, but there is no path from C to D. So obviously, it does not form a cycle. So this graph is acyclic, and since it is a directed graph, it is called as directed graph, acyclic graph. So the answer for both the question is no. There is no path from A to D, and there is no cycle in this graph. Next, we see about connectivity. So now a question will arise among you, what a connected graph is. So when do we call an undirected graph a connected graph? So if we take any two pair of vertices from the set of vertices, there should be a path. If such path exists between any two pair of vertices in a particular graph, then that particular graph is said to be connected. On the other hand, if there is no path between at least one pair of vertices, then that particular graph is said to be disconnected graph. So if you see here, in the first figure, all the vertices are connected, or if I want to reach vertex from any vertex, there is a path. Whereas here, they are distinct, they are not connected. Between two vertex, we do not find any edge, which means I am unable to reach the two vertices from any other vertices, correct? So since there is no edge between any two vertex. If I want to reach any of these two vertex from any other vertices, it would be impossible. So this kind of graph is said to be disconnected graph. So this connected graph is called as complete or fully connected. When do we call it as complete or fully connected? In case of undirected graph, if there is a edge between every pair of, not path, I'm talking about the edge. If there is an edge between every pair of vertices in an undirected graph, that particular graph is said to be complete or fully connected. Understood? So here I have discussed about what a connected graph is about, and what is a strong disconnected graph, and what is a complete or a fully connected graph in case of undirected graph. Now let us discuss connectivity or the connected graphs with respect to directed graphs. Here, so a directed graph is said to be strongly connected or weakly connected. Only we have two terms. We do not. Uh, uh, so disconnected is common for both. Uh, so when do we call a directed graph strongly connected? Is that if there is a path from every vertex to every other vertex, then the graph is said to be strongly connected. So strongly connected or weakly connected is discussed with respect to the path, whereas complete graph is discussed with respect to the edge it has. So if there is a path from every vertex to every other vertex, the graph is said to be strongly connected. Else it is said to be weakly connected. On the other hand, if there is a edge between every pair of vertices, then the directed graph is said to be complete or fully connected. Same as the case we have discussed with undirected graph. So hope you understood the difference between strongly connected, weakly connected, and that with complete or fully connected. So strongly connected or weakly connected deals with the path that the pair of vertices has, whereas the complete or fully connected deals with the edges between the pair of vertices. So directed acyclic graph we have discussed earlier itself. So if a directed graph forms cycle, then that particular graph is said to be directed acyclic graph. So we need not dwell much into it, I suppose. So these are the various representations of graph. So like how we represent tree using array representation, or linked list representation, or list representation. So we represent tree in three forms. One is using array, other one is using list, and the other one is using linked list. Similarly, we have various types for representing the graph as well. So one among it is adjacency matrix. So in the adjacency matrix, the rows and columns are the vertices. The entries of the matrix will be the edges or the connection between the vertices. So in case of undirected graph, if there is an edge between A to B, then there will also be an edge between B to A, correct? Since it is undirected, the edge is two-way. So if there is an edge between A to B, there is also an edge between B to A. So if an edge exists, then entry would be 1 inside the matrix. If there is no edge, the entry would be 0. Now you may see uh, in the particular vertex D, the edge starts from D, and again the edge terminates in the D itself. The source and destination vertex is both the same. Such kind of edge where the source vertex and the destination vertex are same is called as self loop. So this kind of edge is called as self loop. Even if there is self loop, we will mark the entry as 1. Same is the case with directed graph. In case of directed graph, the edges are not two-way. The edges are one-way. So if there is an edge from A to B, that edge will not be considered as an edge from B to A. So here there is an edge from A to B, but there is no edge from B to A. So if you look into the entry, so A, here rows represents the source vertices, whereas the column represents the destination vertices. So from A to B, I have marked 1, but from B to A, I have marked 0. Hope you are clear. So this is how adjacency matrix is used to represent a graph. So you should be able to write adjacency matrix from the graph, or if adjacency matrix is given, you should be able to draw the graph. So it should be vice versa. And this is the incidence matrix representation of a graph. In case of incidence matrix representation, the rows represents the vertices, whereas the column are represented by the edges. So here totally how many edges do we have in this particular graph? Totally there are 8 edges. So we will name it as E1, E2, E3, E4, E5, E6, E7, E8. And there are totally 5 vertices A, B, C, D and E. Here, how to fill the entry is that if there is, so let us take the first one, A and E1. So if there is an edge E1 flowing from A, then the entry would be +1. Or if you take this entry A and E3, it is marked as -1. It means there is an edge E3 which is flowing towards A. So if it is an in degree, or if it is an inbound edge, so in degrees are also called as inbound edges and out degrees are also called as outbound edges. If there is an in degree towards that particular vertex, we mark the entry as -1, and if there is an out degree, we will mark the entry as +1. If there is no edge, you have to mark the entry as 0. Hope you are clear. So this is the incidence matrix representation of a graph. So we have seen adjacency matrix and incidence matrix, and the last one is adjacency list. So this is very easier. So in case of adjacency list, so each entries or each node will be initially totally 4 vertices. So 4 entries would be there. Now see, from A there is an edge to B alone. So from A to B alone. So B is marked as a node. From B we do from A we have only to B. So the from B the reference pointer would be null. And from B we have an edge to A alone. So from B to A, after B is from B we do not have an edge to any other vertices. So the reference pointer is again null, or the address pointer would be again null. From C, if you see from C but vertex, an edge flows to D, also an edge flows to B. So from C we have an edge to B and to B. So either you can mark D first or B first. So C, D, B or C, D, D. After that, there is a no edge. So the reference pointer is null. So both the entries would be correct. C, D, B or C, D, D. Both the answers are correct. From D, we do not have any out degrees or outbound edges. So it is marked null. So this is the adjacency list representation of a graph. So there are 3 ways of representing a graph. One is adjacency matrix, other one is incidence matrix, and the last one is adjacency list. So given any of these 3 types or given any of these 3 representation, you should be able to draw the graph, be it an undirected graph or a directed graph. So now look at this graph. Predict what kind of graphs are these. There are 2 graphs, right? First one and second one. What is the difference that you could observe is, so in the first graph, the edges are simple, whereas in the second graph there are some values mentioned for each edge, right? So the first edge is called as unweighted graph. If there is no specific value, there is no value specified for the edge, such kind of graph is called as unweighted graph. On the other hand, if there is a weight mentioned for the edge, such kind of graph is called as weighted graph. So here, the weight or the value mentioned for the edge does not represent the distance alone. Here in this graph, it is mentioned as 7 miles, 1 mile. So these are the distances. So this weight can be anything. It can be distance or covered, or it can be the cost incurred, or it can be the time lapse, anything. It can be anything. So it need not be specific. You cannot say weight na idu da. It need not be specific. So the first graph is unweighted graph, whereas the second graph is weighted graph. So in the types we have seen many things, right? So what are the types of graphs we have discussed? So directed graph, undirected graph, weighted graph, unweighted graph, connected, disconnected, complete or fully connected, strongly connected, weakly connected, cyclic graph, acyclic graph, directed acyclic graph. So these are the various things we have discussed. There are few other more types also which are not prominent. So I have not discussed those types here. So these are the prominently used types of graphs. Hope you are clear with each types, I suppose. So these are the various applications of graph. So social media is completely based on graph theory. Graph theory is very much essential to understand how social media works. Google Maps, web page navigation, and operating system. So we will see about map coloring problem or graph coloring problem in the later part of the lecture series. So these are the various applications of graph. Hope you're okay with this graph terminologies and representation of graph. So we will meet in another lecture on another topic of data structures. Thank you.